All right, everyone, so here's our example of a series circuit done mathematically. So we're going to be mindful of the big ideas with voltage and current that we learned in the last video that I did with FET. But then I'll teach you some new ideas too. So first thing, it's not absolutely necessary, but I like to indicate the direction of conventional current. Positive terminal here, so my conventional current's going to go clockwise. Really not necessary, but it's just a good habit to form. And then if I think about it, some of the rules with voltage was, well, voltage is like pressure, whatever the battery gives. In this loop that I take with current, because there's only one path, it's a series circuit, I better lose that 30 across these as a combined amount at least. The tricky thing is though, it doesn't split evenly 10, 10, 10 for the voltage because you can see the resistors, they're not identical. I've got 2 4 ohms and 1 2 ohm. So I can't just assume anything. The other thing is we do know, good news, that the current will stay the same because it's the same path, so all these currents should be the same, but I don't know any of them, so I can't fill in the blanks. So there's one last idea that I didn't teach you in the FET, and it's related to total resistance. In a series circuit, this is really nice actually, the total resistance is just the sum of the resistors, however many there are. So the idea is the more resistors you add in a series, the more total resistance there will be, and ultimately lowering the total current. Sorry if it keeps shaking, guys. I got on my table and it's kind of wobbly. Anyway, though, since it is in series, this is really easy. Total resistance, and there are 3 resistors, is 2 ohms plus 4 ohms plus 4 ohms. And so my total resistance is then 10 ohms. All right, not too bad. So you'll notice I really like to organize stuff neatly up here. For instance, all the total informations I put by the battery, and I've labeled all this individually. You'll see why in a second. Why the total resistance was so helpful is because the other thing we're going to be able to use besides the kind of rule with voltage, current, and now total resistance is we're going to be able to use Ohm's law. V equals I times R. There is one major rule that you must follow with this though. You have to match subscripts. You can't mix and match. So you can't do total voltage with resistor 1's value. The problem with that is if you did do that for each one of these resistors, you would get 2 different currents, which disagrees with what we learned about series circuits in terms of the current staying the same. So if I'm going to solve for total current, I need to use total resistance and total voltage. So with that being said, I can plug in 30 here for total voltage, 10 for total resistance, and solve, and I get a total current of 3 amps. I'm not going to solve out that math for the sake of time and space on here. I think you guys can do that in your work. That's pretty simple. All right. Now you might be like, well, yeah, we could do that for this because there were 2 knowns, but we can't do it here because there's only 1 known. I agree, you can't do Ohm's law, but this is again where the rules that we learned come into play. It's a series circuit, so if there's only one path, the current should stay the same. So this should also be 3 amps, this should also be 3 amps, and this should also be 3 amps. And now then, of course, you have 2 knowns here, so I can actually do Ohm's law again. But again, being mindful of the subscripts, if I want to solve for voltage 1, I got to use current 1 and resistor 1. So if I plug those in there, I get 6, and the units would be volts. Over here, multiply, I get 12 volts, and over here, same thing, 12 volts. All right, if you think about voltage, though, voltage is a pressure, and batteries give pressure, light bulbs or resistors will take. So these are actually drops if you want to add the negative. I won't be picky if you don't. But then what's really cool about circuits is there's something that we haven't done that will always happen with these, where if you do it, it'll check to see if you got 100%. So we use Ohm's law for every single thing. And I use the current rule, which we call the loop rule, or excuse me, junction rule, my fault. We use the current rule, the junction rule, saying, hey, there is no junction, the current's all the same. The one thing we didn't use was related to voltage. And this is called the loop rule. Sorry, I mixed them up. And the idea was that whatever the battery gives, in this loop that I travel across, the light bulbs must take. So even though it didn't split 10, 10, and 10, these should still add up to 30, which 12 and 12 is 24, and 24 and 6 is 30. So right there, I know I'm all good. All the rules check out. Current's the same. Voltages add up to the battery, and that should be all good. Okay? All right, when you guys do the problem that I assigned you, make sure you show your work really organized like this. You can just take a screenshot of it at the end. All right, give me a little signature in one of the corners. All right, so I would just be like, hey, it's Mr. Bank. That way I'll know it's actually your work and you didn't just send it to a friend. Unfortunately, I can't trust you guys, man. I'm just losing it. Kidding. But show your work really organized like this. And again, you can always refer to the textbook for help too, or even just check it on the website if you want to, okay? Good luck with this, guys. Remember, there is a discussion forum if you want to ask me any questions, okay? Bye-bye.